Hi everyone, welcome to our video on limits, where we'll be finding limits using graphs and tables. Well, to start off, let's break down a little history of where the idea of limits came from. And this is supposedly like a legend. It could have happened. Who knows? All right, so it involves Newton and his apple. Well, it's said that one day that Newton was sleeping under an apple tree, and he was awoken because an apple fell on his head. And then he thought, well, wonder how fast that was, because it kind of hurt. And he started to think, well, if an apple fell and hit me on the head, it had to travel a distance. And over that distance, it would take an amount of time to travel. And, well, I can calculate that velocity. So velocity equals distance over time. Okay, so over some distance, over that, so he can measure that distance, and they could use some crude method to measure the time, and they could say, all right, that velocity is equal to the distance over the time. So miles per hour, whatever it hit me at, I now know. However, this is based on an average velocity. So it's over a length of time. What he wanted to know was the exact speed that it hit him. And so what he did was he shortened this length, and he said, all right, what if I could just measure, so it's already falling, and I can measure it a shorter length. Okay, so still, it starts to become more accurate to the instant that it hits him, because, well, the apple is not really moving that fast yet right when it drops from the tree. As it progresses down toward the ground, it's traveling faster. Okay, so and you can imagine that if you've ever played with a baseball or any type of ball, you know, the higher you throw it up, the harder it's going to come down, because the gravity is getting more of a effect on it. Okay, so anyway, so he's saying this at least is more accurate now, because it's really only focused on the faster speeds. But again, it's still an average velocity. It's not the exact speed that it hits me at. And so then he thinks, well, what if I shorten it again? And then, well, again, that's still an average velocity. It's getting closer. And then he thinks, all right, what if I really shorten it? What if I keep shortening it to where there's barely any distance at all? Okay, so then that is getting very close to the exact speed that it's hitting him at. However, if there's hardly any distance traveled, that means there's hardly any time that has passed as well. So the closer that it gets to being such a small margin means that the time is getting close to zero. So we say the time is going towards zero. Well, if you have zero in a denominator, that's an issue. So if it was some type of distance divided by zero, well, that's undefined. You can't divide by zero. And so he thought, well, I know I don't want to get it to be exactly zero. I want to use something that's very close to zero. And then that's the idea of the limit. So the limit is saying, how about instead of dividing by zero, we divide by something that is very close to zero. We divide by something very close to zero. And then that would still be allowed. So he's talking about, like, if we divide by something like this, bunch of zeros, and then throw a little 1 at the end. So this is very close to zero, but it's still a number that's not zero, so that means you could still divide. Okay, anyway, so that's the idea of the limit. So the idea of the limit is as if we are able to divide by zero, where we usually would be saying, hey, that's undefined. Okay, so I hope that helps explain a little bit of what's going to happen. But before we get into other applications, okay, so this was a physics one, and we'll be doing some business ones mostly, but physics is where it came from, and Newton then went on and kind of created physics as we know it. All right, anyway, but let's break down how these limits work. All right, so I'm going to skip reading this. This is if you're just kind of following along the notes by yourself. I'm going to go straight into how we would break down finding limit problems. Okay, so and the way that it's written is shown in 2, 4, and 6. But anyway, let's see how we can break this down, and we'll explain as we go. So it says, use the graph of f to determine the following, if possible. All right, so this is f of 3. Well, f of 3, that's saying that's an x coordinate. So follow your pink curve where you see 3. All right, so 1, 2, 3. So here's my x coordinate, and then from here, well, the x coordinate, there's 3, 1. So it's saying where I have x is equal to 3 gives me y equals 1. So remember, your f is giving you a y value. So that is a y value right there. So when x is 3, y is 1. Okay, and then the limit portion of it, the limit portion is saying, all right, how about, so I'm going to do blue on this to show what I want to mark on the graph. The limit is saying, all right, you're gonna start on the graph. This is saying the limit as x, let's write it in words, the limit as x approaches 3. So that's that portion. The limit as x approaches 3 of our y coordinate. So f of x again, where we want to get a y value. So our answer is still going to be like a y value. And let's go ahead and just box it up. Okay, so we'll leave it blank. So this will be a y value. Okay, anyway, so all it's saying is, well, the limit as x approaches 3. So we want to follow our graph. So I want to start somewhere on the graph, and I want to follow it as close as I can until I get close to x equals 3. And I want to do that from both directions. So I'm there on the left approaching it to get here, on the right approaching it, and it looks like as I get close to x equals 3, well, the y coordinate looks like it would be 1 still. So it's just 1. Okay, so this is an example where our defined f of 3 matches our limit. So sometimes they are the same. Okay, so that's all we're doing. One other way I think of it is if you're a person and you're walking on this graph. If you're walking and you want to get to x equals 3, where would you step as your y coordinate? So from both directions, if you're walking and you step at x equals 3 and you're asked, hey, what do you think your y value is? Well, right there you could say, well, it looks like it's 1. Okay, anyway, so let's see these other scenarios. So on our number 3 here, f of negative 1. All right, so f of negative 1, well, here's where negative 1 is on the x. And then I want to follow my graph. Well, notice I have an open dot here. That means the graph is not defined right there. So I don't want to say that this is 1. That would be incorrect. Instead, I want to go to where it is defined, which is this solid dot. So let me go ahead and just make that extra bold. So this is the solid dot. That's where the function is defined. So solid dots are where it's defined. Right there, the function's undefined. Okay, so okay, so undefined versus defined. And then, well, I can see what the point is. It is negative 1 and 1, 2, 3. It looks like it's 3 up. So negative 1, 3. And then, well, again, that's my x coordinate, negative 1. 3 is the y coordinate. So that is the answer for this one. Now, our limit as x gets very close to negative 1. So let me do this one in green. Again, it should equal something that's like a y value. So our limit is just saying, hey, this is going to be a y value. There's our x value. So if we have x going into something, we should get a y value out of it. All right, and as we get very close to negative 1, again, it's the same thing where it's like I'm a person and I'm walking on this from both directions. If I'm walking and I get close to negative 1, we would say, hey, what do you think you're about to step on? Okay, well, this person would say, hey, I'm about to step on 1 as a y coordinate. And so that's it. From both directions, this person would say, if I'm walking up or down this, I'm about to step on the y coordinate of 1. So we wouldn't think if you were blindfolded and you were walking up this hill, you wouldn't think your next step would shoot you up here to this dot. No, we would think it would progress like stairs and we would just step right here. Okay, so it's okay that it's undefined. It's still just telling us this is where we think we're going. That's where the limit is headed toward. That's where our function looks like it's going to. And so that's what we answer this as. Okay, so notice the main difference here. So this time around, these answers do not match. That's okay. Where your function is defined can differ than your limit. Okay, and then one more here for this graph, f of 2. All right, well, f of 2, again, this is an x value, this 2. And then so here's where 2 is as an x, and I see, oh, it's just an open dot. And so I don't see any other solid dots anywhere. So that means this is undefined. And we probably want to write equals. Actually, let me scribble that out. We would say is undefined. And I'm using U and D for undefined. Okay, so f of 2 is undefined because there's no solid dot anywhere on our positive 2 x coordinate. So on that vertical line there, there's no solid dot. Okay, so that means it's undefined. However, the limits could still exist. So let's do this one. I'll change it to red. So we're going to do this one. So it's saying as the limit as x gets close to 2. So again, if I'm like on this curve and I'm following it, red's a little tougher to see. But if I'm following it, if again, you could use the person as the thing if you need to. If I'm following it on either way, if it's like a hill and I'm walking along this hill, we would say, hey, if I'm about to step right here, what do you think that y coordinate is? All right, well, it looks like the y coordinate this time is -1. Okay, so it's saying where this graph looks like it's going to, again, regardless if it's defined or not. So it's where is this looking like it's headed to? That's it. Okay, so that's a quick preview of our limits. So this is it graphically. So the limit as x gets close to 2, we're saying this again is a y value. And what it's saying, so our y value, so these aren't actual defined y values. We're just saying similar to this, as x approaches 2 or as x gets very close to 2, our y value is approaching that -1. So y value approaching -1. So it looks like that's where that's headed toward. Okay, so anyway, so I hope this is helping. Let's look at another problem. Okay, so this time around we have a table, and they gave us an actual function where 3x squared minus 6x over x cubed minus 8. So they wrote f of x down below. So there's our f of x. And we have, so let me just kind of put that. So that is our f of x right there. And remember, f of x is the same as y. So on this problem, it says use a table to find it. Now, if you have a calculator, a handheld calculator, that's fine. For most of the problems, I'm going to use this. Okay, and this is what is, I think, very easy, especially since you're online anyway. All I did was type in Desmos, and it gives you these options. I think just going to the graphing calculator is the best. The scientific calculator can also work okay, but I think the graphing calculator probably is the best tool for us. Okay, so I'm going to click on the graphing calculator, and then now I'm going to type in this function that we have, so that f of x, into this. And before we do that, though, let me go ahead and say, remember that there's implied parentheses. So let's put those parentheses on there, and that makes it easier to plug in here. Okay, so, and I'm just going to type it in exactly as I see it. So parenthesis 3x and then shift 6. So that they call it the caret key. So shift 6, that little up arrow makes that happen. So 3x squared and then right arrow minus 6x parenthesis divided by parenthesis x shift 6 to get the up arrow cubed right arrow minus 8 parenthesis. Okay, so there's our function, and with this we could see that we could see the graph of it. So we can see that, and notice it has some gray dots there. So the 2, it has the 0.5, but it said in this problem, so you could use graphs to help you as well. But on this problem, it said to make a table for our scenario. So let's go ahead and make a table. And on this problem, they gave us the values to plug into the table. So to do that, on this problem, I'm going to go to the edit list, and I'm going to click on convert to table. Okay, and then now I'm just going to type those values in. So I've got 1.9, enter, and then I've got 1.99, enter, and then 1.999, enter, and then it said to use 2, which is undefined because notice if you were to plug 2 into the denominator, you would have 8 minus 8, which is 0, so you can't divide by 0. Again, so this limit is what we're trying to find is where it's close to 2. Okay, and then let's plug in those other ones, the 2.001, enter 2.01, and 2.1. Okay, so my focus is just these values here. And we have them all, and what we want to see is, well, what's happening as our x gets closer and closer to 2. So at 1.9, it's sort of close. 1.99, it's getting closer. 1.999, it's getting really close. And notice what's happening with our pattern here. These are our y values, the 0.4995, and then 0.4999995, and then this one, 0.49999, a bunch of 9s, and then a 6. Well, we can kind of start to see the pattern. It looks like the more 9s I put after this value of 1, so 1.999, if I keep adding 9s to it, it's certainly looking like it's just going to be 0.49999 with more 9s on this one. Okay, and then same deal with our 2.1. So 2.1's sort of close to 2, and we get this value. 2.01's a little closer. Notice there's more 9s after the 4. And then 2.001's really close, and we get 0.499, a bunch of 9s as well. So it looks like as we get close to 2, from either direction, it looks like it's starting to kind of probably round to 0.5. So you could think, hey, if it's 0.4999999 forever, we'd probably be able to assume that it rounds to 0.5. Okay, so that's what's happening on this problem. So it looks like our limit, and we could also kind of see it in our graph. Let me go ahead and click that to get projector mode so it's a little bigger. And those are all my dots, but look at this. So it says it's 2, even on this graph, it says it's 0.5, 2, 0.5. Now, the table disagrees. It really is undefined at 2. So 2, it is undefined. However, it's looking like, based on these values of decimals, it's getting so close to 0.5 that this program is just saying, hey, yeah, it's probably just 0.5. Okay, again, even though it's truly undefined. Okay, so what this is saying is the limit of that function. Okay, so let's go ahead and just kind of copy these to down real quick. So I'm going to just move this over so I can see it, and we'll copy them down. Okay, so we had, let me start with 2. Notice it was undefined. If you try to plug 2 into this, it's all undefined. So in our function, f of 2 is undefined. Okay, but if we plug those other ones in, we got 0.49956. We'll do 5 decimals. And then 0.49999, there's 5 decimals. And then this one is really, if it's to 5 decimals, at this point it does round to 0.5. And then similar, 2.1 is kind of far away. We said that was 0.49960 to 5 decimals. And then 2.01 is 4.999, like that, and then at this point it would just round to be about 0.5. Okay, so as our x is getting close to 2, so this is our x is approaching 2. So as x gets close to 2 in both directions here, it looks like it's headed toward 0.5. So these are starting to look pretty much the same. So that means this limit then, the limit as x goes to 2 of this 3x squared minus 6x over x cubed minus 8 is headed toward those decimals right there of 0.5. Okay, so that's using a table to find a limit. And also, again, you could also use the graph, which is nice as well. The visual helps out as well. Okay, so that's all it is. It's just, again, saying what's the y value getting close to as your x value is getting close to 2. So as x gets close to 2, our y is getting close to 0.5. Okay, anyway, so let's do one other thing in this. Okay, so again, well, let me break down these. So on this problem, from the left side is left of 2. From the right side is right of 2. So these ones that are bigger, we need these two to make a match to find this limit. However, you could do them separately. We could look at just the right side, and we could look at just the left side if we want. Okay, so what we have here, so again, I'm going to kind of skip breaking these down. Let's just go straight to the problem and say what we want to do. And notice we've got a lot this time. Okay, so it's use the graph of f to find the following values or state that they do not exist. If a limit does not exist, explain why. All right, so let's break all these down. So f of negative 2. All right, so negative 2 is right here as an x coordinate. And then I see, I have an open dot, so not that one. Solid dot, 3. So where my negative 2 is x, my y coordinate is 3. So this is just 3. Okay, and then our 2, 3, and 4 all involve the limit as x getting close to negative 2. So I'm gonna do these in blue, kind of group them together. I guess I could have done that one. Let me just so these are all the ones that have x being close to negative 2. Okay, what this one means, so this is saying the limit as x gets very close to negative 2 from the right. So that little positive symbol means from the right. From the right. Okay, so that means find where you have negative 2 and then go a little bit to the right. So I'm somewhere about here. And then now get as close as you can to negative 2. So as I get as close as I can to negative 2, it's looking like my y coordinate's headed very close to negative 4. So this is negative 4. Again, you could use the same style that we did in the previous graph if you wanted. So this one's a little tighter, I would think. So here's my long-necked person here walking, and if they're stepping or if she's stepping, they're gonna step on negative 4 as a y coordinate. Okay, so if they're blindfolded, they all of a sudden wouldn't magically jump up there. Okay, so if they're just walking along this curve, they would assume that they're going to step right there, which is a y coordinate of negative 4. Okay, and then for number 3, this little negative symbol means from the left. From the left. Okay, so from the left would be find your negative 2, go a little bit left somewhere, and then now follow the curve. Okay, so the blue on blue is a little tough, but I'm going to bold it. Okay, so from the left, and then get as close as you can to negative 2. Well, again, if this is a person walking, they would assume they're going to step on a y coordinate of negative 4. There we are. Okay, and then now with number 4, the limit as x goes to negative 2. So that means from the both right and from the left at the same time. Well, all you have to do is look at these two answers. If these two are the same, which they are, negative 4 and negative 4, then all you have to do is just copy that, and that's it. Okay, so from the left and from the right, it's going to the same negative 4. Okay, so let's see our other one. So let's do this one in green. So all of these, so I'm going to circle them, I'm going to group them, because they all involve x going to or being 1. Okay, so when x is 1, our function looks like it's open dot and open dot, so it doesn't look like it's defined anywhere. So this one is undefined. All right, and then now I'm looking at this. So from the right, so as x goes to 1 from the right, so find where 1 is, go slightly right, and then start heading back toward the 1. Okay, well, if I'm a person and I'm walking on this line, I would think, hey, if I'm going to walk along this hill, I would step on this y coordinate of 0. So that's 1, 0, and I want the y value right there. So from the right, I'm thinking I would step, if I'm blindfolded along this, I would assume I'm going to step on y equals 0. Okay, so that was number 6. Let me go ahead and label. So there's number 6. Number 7 is from the left. So here's 1. From the left would be putting me up on this part of the curve, and then I'm walking toward x equals 1. And as I walk toward it, well, I would assume I'm going to step on this y coordinate of 2. So this is 2. Okay, so this is number 7 right there. So this is the left of it, this is right of it. Okay, so again, I'm blindfolded. I would think I'm going to step on this when I'm at x equals 1. So I'm very close to it. After 1, it looks like I'd fall off a cliff. Okay, so, but right now I'm thinking I'm going to step on that y coordinate of 2. Okay, and then to answer this from both the left and the right, I have to look at these two answers. Because these two answers are different, that means this one does not exist. And we will write D and E for short for these limits. So this limit does not exist because our answers from number 6 and number 7 were different. Okay, so we're going to say the left-hand side limit and the right-hand side limit, or let's write it like this, the right-hand side limit did not equal the left-hand side limit, or let's just say the left side limit, since I'm running low on room, like that. So the right-hand side limit did not equal the left-hand side limit. That's why this one does not exist. Okay, so these two have to be the same for this to have an answer. Okay, anyway, let's do one last one here. One last part. I'm going to do them all in red because they're all about 4 for x. Okay, and looking at this, well, when x equals 4, my function is defined at y equals 4. So this is 4. Okay, and then now same thing where I'm looking for the right of 4. That little plus tells you go right of 4. So I'm somewhere over here, and then I'm getting as close as I can to x equals 4. Well, from the right, as close as I can, looks like my y-coordinate is 6. Whereas on my left side, so the little negative from the left of 4 puts me somewhere about here, and then I want to get as close as I can. Well, it looks like I'm headed toward y equals 4. Okay, and then for number 12 here, as the limit as x goes to 4, I have to just look at these two answers. Because 6 and 4 are different numbers, I would say that this one does not exist. Okay, and the reason why is, well, let's write it like this. The limit as x goes to 4 from the right of that function does not equal the limit as x goes to 4 from the left of that function. Okay, so that's why this one does not exist. So that's all you have to do. So if they are the same, like in the first grouping of blue, so if these two numbers are the same, then this limit is a match for those. Notice it doesn't matter what this one is. So this one was different. The f of -2 was 3. That's okay. All I care about is these two when looking for this answer. So from the right side, from the left side, combine to make it from both sides. Okay, so there we go. So there's that scenario. Okay, and where this is going to end, so I'm going to pause the video. We're going to start up here on the next video. But so far, when doing limit problems, we either use a graphing calculator like we did for this one, or we use a graph, like these ones were already given as a graph, so we were able to do it from what they gave us, or we create a table of values like we did on this one with a calculator. Okay, so we made the table of values. And then lastly, we have algebra techniques. Okay, so that means we could do it without any type of technology. Technology could help though, so we'll still use it every now and then. Okay, anyway, so these are the 3 ways. So whatever it is, just remember that limits are still like finding a y value. Every time it's like finding a y value. And that's all they really mean. Okay, so don't let the notation freak you out. All right, anyway, so that's it for now. Thank you for watching, and I will see you next time.